Alright, in this video I'm going to talk about the speed required to make two objects get really close together. In this case we're going to just sort of pretend like we have two protons that are going to try and do fusion. We'll say that we have to get them within 0.0012 nanometers of each other. That's a little ridiculous. I just made that number up. I made it really small, but when I'm looking at it again, I'm guessing it's probably not even small enough to really make two particles fuse together. So don't really take too much into that number. I just sort of made it up. Anyways, assuming that we have two protons that are flying at each other, determine the minimum speed that we would need to get them that close together. So here's a proton, here's a proton, we're shooting them at each other. We're trying to get them within 0.0012 nanometers of each other. Again, that's just some made-up number. It doesn't really have anything to do with the fusion process. Mass of a proton is equal to 1.67 times 10 to the negative 27 kilograms, or something close to that. And the charge on a proton is equal to 1.6 times 10 to the negative 19 coulombs. So what we're going to do here is we're going to give these two protons a whole bunch of kinetic energy. So we'll have EK from proton 1 and EK for proton 2, and we're going to convert that into an electrical potential energy associated with the repulsion that they would experience if they were that far away from each other. So EK1 will be 1/2 mv squared, and EK2 will be 1/2 mv squared, and the potential energy we're creating here is KQQ over R. Now we're going to assume that they have the same mass and the same velocity, since they're both protons, and we said in the question they're going at the same speed. So 1/2 mv squared is the same m and the same v, so we can just make that 1/2 plus 1/2, so that just becomes mv squared. And that's going to be equal to that potential energy. Now I'm going to divide both sides by mass and square root, and I can see that the velocity that I'm going to require is going to be equal to KQQ over mr. So now I just have a big substitution to do. Square root of 9 times 10 to the 9 times 1.6 times 10 to the negative 19. Again, because they're both protons, divided by the mass of a proton, and that minimum radius that we made up. I think it was 0.00, I don't know why this does this sometimes, 0.0012 nanometers. Sorry about all that resizing, just trying to get it figured out. .0012 nanometers means times 10 to the negative 9 meters. Alright. So my final answer here is going to be 3.4 times 10 to the 6 meters per second. So they'd have to both be going that fast to make it work. There's an interesting thing about this. You can watch other YouTube videos about how quantum tunneling is actually involved in the fusion process, and so this whole calculation is a little bit misleading, but still sort of interesting to give you an idea that they would obviously have to be going very, very fast to have any chance of participating in the fusion process.